Hey everyone, this is Dr. Reza. For your information, this week I won't be around. Therefore, I have recorded this video as a replacement for this week's lecture. Please watch this video in your free time and let me know if you have any question. If you didn't understand any part, you can ask in our next class. But it is compulsory for you to watch the video within the period of time that is given for the lecture in this week. In our previous class, if you remember, we talked about influence line and how they can be used in order to estimate maximum shear force, bending moment, and also support reactions. We saw a few examples. So today I'm going to give you two more examples in order to get more familiar with the application of influence line for the calculation of maximum reactions. These two questions that we will see today are the questions that were given to students during past 2 semesters as their question for test 2. So this semester, more or less, almost similar questions will be given to you. So try to learn these two very well. Okay, let me enlarge the page so that we can see the questions very well. Okay, I will zoom inside the first part. Okay. Okay, in the first question, we have a two-span beam, as can be seen from the screen. The beam in the first span has one internal hinge at point B, and it is clear that the span length is 5 meters. AB to BC is 4 meters and 1 meter, and CD is 5 meters. The question first asking us to draw the influence line for support reactions, RA, RC, and RD. And then it is going to be also a second part for this question, which is calculation of maximum support reaction at point C and maximum shear force at point C. Actually, this one should be B. It is mistakenly written to be C, so it should be B. Please correct it inside your note. And these maximum forces or reactions are going to be calculated due to two loads. One is going to be a moving load, 2-point loads with a distance of 1 meter is our moving load. And we have a self-weight or dead load that is going to be all over the span. Okay, the first part, as we said, is derivation or development of influence line for support reactions. If you remember, for the development of support reactions, influence line, we said we have two approaches, quantitative and qualitative. And in our previous class, we learned how to draw influence line based on qualitative approach, which was firstly developed by Muller-Veslov. We said if you want to draw influence line for support reaction through qualitative approach, the first thing that you need to do is to remove the support. Here we want to draw the influence line for support reaction at point A. So our first job is to remove the support. So the moment that you remove the support, the second step is to impose a unit displacement to the location of the support, and then look into the deformed shape or displaced shape of your beam. So if we do that, you can see point A is going to move toward up, and then point B is connected to point A through an internal hinge. So if you have a hinge, you know that we can have easily a rotation in that location. Therefore, point B can rotate. However, for point B to be able to go up, we need to see whether point C allows it or not. So if you look carefully to the rod BD, it is connected to two roller support, and this roller support basically impose a reaction to point C and D. Therefore, if point B wants to go up, point C and point D does not allow it because they are pulling down the rod. Therefore, our influence line is going to look like a triangle with a maximum of 1 at point A and reaches to 0 at point B because point B cannot move as point A goes up. So this is going to be the influence line for RA according to a qualitative approach. For RC, again, we can apply the same technique. So in order to draw the influence line for RC, first thing that we need to do is to remove the support reaction, impose a unit displacement to point C, and look into the displaced shape. So if you look into the right side of point C, we have only one support, and it is a roller support that can rotate. Therefore, the moment that point C is moving toward up, since point D has a support reaction that doesn't allow it to go up, it can only rotate. Therefore, we are going to see for the right side this displaced shape like the one that I draw here. For the left side, we have point B here that has a hinge and point A. So if point B wants to go up, we should see whether the adjacent point allows it or not. As you can see, we have only one pin support over there, and point B can easily move toward up as point C moves because it can rotate. And since we have only one support, meaning the support can rotate in that location, therefore at point A, we are going to have a 0 value for our RC influence line. So the displaced shape due to the unit displacement that we applied to point C is going to look like the shape that I draw here. So you can see the value of point B also can be easily calculated by using the mathematical equations, which equals to 1 point. Okay, now we can go and draw the influence line for point D. So at point D, we have a roller support. We remove the roller support, we impose the unit displacement, and then we look into the deformed shape of other part. So if point D goes up, point C, since it is a roller support, cannot move, but it can rotate. However, for point B, in order to move up and down, we need to see whether point A allows it or not. Since we have only pin support, that means the moment that point B goes down, we can have rotation here because we have a pin support. Therefore, the deformed shape is going to look like the one that I draw here, meaning at point C we reach to 0. Point B is going to go down the moment that we impose the unit displacement to point D. And then at point A, again, we reach 0. So this is going to be the values for the important points of the influence line at point D. Okay, so you can see it was not too much difficult through the qualitative approach to draw the influence line. And since we need to calculate VC max, so we need to draw the influence line for, VB, we need to draw the influence line for point B as well. If you remember, we said for shear force, if you want to draw the influence line through the qualitative approach, we are going to put one internal roller inside the location of interest. And then we are going to impose a displacement to that location. Left side of this roller is going to move toward down, and right side is going to move toward up. And then we are going to look into the displaced shape. So if we look into the left side, we can see we have a pin support that can rotate. So if point B goes down from the left side, point A can easily rotate and come down. However, for the right side to go up, we need to see whether this rod can move or not. So you can see similar to the first case that we explained, since we have two roller support that impose the reaction to point C and D, and we are not allowed to have any bending inside our element. So if point B wants to go up, point C should go up. That is not possible because we have a reaction over there. Therefore, the influence line for shear force at point B is going to look like the one that I draw here. Right side doesn't move, therefore the value will be 0, and left side can move down. And since the imposed displacement again equals to 1, and it's going down, it becomes -1. So this is going to be the shape of influence line for VB. Okay, now that we got all the influence line, we can go to the second part of the question, which is calculation of maximum RC and maximum VC. So if you look at RC, you can see the graph has only positive values, meaning we don't have any going down in the influence line that makes the area negative area. Therefore, under both loads, moving load and self-weight, we expect to have a positive value. So first we need to calculate how much is the value of RC when we have a self-weight over there. And then after that, we are going to put our moving load to the location that gives us the largest value. So for self-weight, since it is always all over the span, the self-weight is going to impose its effects to the whole area. So we just need to calculate how much is this area here and multiply it to 15 because the intensity of load is 15. So that is going to give us support reaction due to the uniform load. And then for the point loads that are moving, if you look carefully to the graph, we can see the highest value of influence line is when the load is at point B and the intensity is 1.2. So the best case is to put this 10 kilonewton exactly at 1.2. And the distance between two loads is given to us constant value of 1. So 1 meter after that, we reach to point C. And at point C, the height of the influence line is 1. So 10 multiplied by 1.2 and 5 multiplied by 1 is giving us the reaction of RC due to the moving load. So you need to sum it up with the value that you get from the uniform load, and that would be the RC max. This is what we have done here. So you can see we have calculated the area. We have two triangles, 4 multiplied by 1.2 divided by 2. It gives this triangle, and 6 multiplied by 1.2 divided by 2, the second triangle, and multiplied by 15. This side is the effect of uniform load, and then 10 multiplied by 1.2 and 5 multiplied by 1 is giving us the effect of point load. And totally we get 107 as RC max. For shear force, we do the same calculation. So we have uniform load again, and we have our moving load. If you look at the influence line of shear force, you can see the value is going to be always negative because we don't have any positive side inside of our influence line. Therefore, we are going to have the effect of uniform load, 15 kilonewton. Since this side doesn't have any area, so we have only this area to calculate and multiply it to 15. So this area is, the length is 4 meter multiplied by negative 0.1 and multiplied by 0.5. And then when the area was calculated, multiplied by 15. That will be the shear force due to the uniform load. And then we need to see the worst case scenario for the point loads. You may investigate two cases. One of them is shown here. When 5 kilonewton force is at point B, as exactly at the internal hinge, and 1 meter behind it is the 10 kilonewton. So this is going to be 10 multiplied by negative 7.5 and 5 multiplied by negative 1. So 7.5 plus 5 gives you negative 12.5 in this scenario. Another scenario is the time that maybe you have only 1 point load applied to the location of internal hinge, meaning the moving load is moved and 5 kilonewton is at the support and 10 kilonewton is exactly at the joint. So for that scenario, you have only 1 point load that is acting on the influence line. So it's going to be 10 multiplied by negative 1. It gives you negative 10. Since the first scenario gives negative 12.5, larger than the second one, so this is going to be the worst case scenario. So according to these calculations, we have the area multiplied by 15 due to the uniform load, negative 0.75 multiplied by 10, negative 1 multiplied by 5, and totally negative 42.5 is the maximum VC for this structure. Okay, so this one was for the case that we had only 2 point load, and it was our first example. Now let's go and see the second example. Second example is more or less similar to the first one. The only difference is that our beam is going to have two cantilever parts. So the span length is given to you 2 meters, 6 meter, 4 meter, 10 meter, and 2 meter. And again, our beam is going to be subjected to two different loads. One is self-weight, which is going to be all over the span, and another one is moving load that has 2-point loads of 5 and 1 kilonewton. And the distance between these two is 3 meters. So just keep this in your mind that when this is given 3 meters in the exam or test, you cannot change it, and you cannot separate them. That means these 2-point loads are moving together with a distance of 3 meters. Sometimes in the exam, we may also give you a moving uniform load. For example, something like this with the intensity of 5, and the length also is given to you, let's say 5 meter or 4 meter, whatever. So if you have two different live loads, you need to consider the effect of both of them in the worst case scenario and calculate the maximum and minimum based on that too. But for this example that is given to our student, at this time you have only one moving load. But it doesn't matter how many moving load you have, each one of them should be placed in the critical location, and after you calculate the effect of each one of them separately, you sum them up, and at the end you get the total effect. Okay, let's see what it was. In this example, we need to draw the influence line for RB, RD, and RE. And then the question is asking for the maximum. Also, we need to draw the influence line for VC and ME. And we need to calculate maximum VC and maximum ME. So first, let's draw the influence lines for support reaction. As we said in our previous example, we said in order to draw the influence line for support reaction according to the qualitative approach, we need to first remove the support and impose a unit displacement to that support, and then look into the deflected shape. So if you look carefully to point B, you can see the moment that we shift point B up as much as 1 centimeter, for example, the point A also is going to move accordingly to the upper level because it is connected to point B. However, for the right side, we need to see how it's going to be the displaced shape. So if I shift point B up, in order for point C to go up, the rod CE also should be able to rotate or go up. But if you look carefully at point D and point E, we have some support reactions that doesn't allow point C to go up. Therefore, at the moment that point B goes up, we are going to have only rotation at point C. So our influence line is going to look like this shape. And the maximum at point A equals to 1.33. And after point C, we have 0 values for our influence line. So if you want to draw right now the influence line for point D, meaning support reaction at point D, again, we can use the same technique. So here we are going to remove support reaction, impose a unit displacement, and then we are going to look into the displaced shape of our structure. The right side of point D has only one support reaction, and it is a roller that can rotate. So if point D is moving toward up, point E cannot rotate because at point E we have point E cannot move up because at point E we have a roller support. However, point E can easily rotate when point D is moving. So we are going to have a displaced shape similar to this one. If this point D goes up, point E is going to rotate, and the cantilever part is going to go down. Now let's look into the left side. Point C is directly connected to point D. Then in order for point C to rotate and to go up, we need to look to the backside to the adjacent point. Here we can see we have only one support. And this support is not a fixed support, it is a pin support. Therefore, pin support can rotate. Therefore, the moment that point D goes up, actually point C also can go up together with it. And we may have some rotation at point C. And at the same time, at point D, we are going to have some rotation, and the rod AC is going to have an inclined shape similar to this one. So according to this calculation, you can easily obtain the values for the points that we don't know based on mathematics. So this is going to be the influence line at point D. Now let's go and draw the influence line for point E. At point E, again, we have only one roller, and we are going to remove it. The moment that you remove the support reaction and impose a unit displacement, you need to look into the displaced shape of your beam. So point E is moving toward up, and the end of cantilever can easily move together with it because they are connected to each other and there is no any support after that. However, for point D, we need to see what is the condition. Point D, if it wants to move, it's not possible because point D is a pin support, but it can rotate. It can rotate. And then for point C, we have an internal hinge. So point C, if it wants to go up and down, it depends on the condition of point B and D. Since both of them are pin and roller and they are allowed to rotate, therefore point C can easily go up and down. Now we have a situation in which point E is shifting itself toward up, and then at the same time, the beam is going to rotate at point D. And the moment that it rotates at point D, when it reaches to point C, again, we are going to have another rotation. Oops. Okay, so it's going to look like this one. And then from there, we are going to have something like this. Sorry, I draw it not very well. I draw again. It's going to have a rotation from here. And then after that, it's going to move like this. So this is going to be the displaced shape of our beam if we have a unit displacement at point E. And then after that, from mathematics, you can easily calculate how much is the value in the beginning and in the middle of your beam. Now we have already obtained the influence line for support reactions. Our next task is to get the influence line for shear force at point C. So according to what we said in the class, when it comes to shear force influence line, we need to have one internal roller at that point and impose a unit displacement such that the left side of that roller goes down and the right side goes up. And then after that, we need to look into the deformed shape. So if point C wants to go down, we are going to have a rotation at point B, and therefore we see something similar to this one when we push left side down. However, for the right side to move, we need to see whether this rod can move or not. So again, you can see we have two support reactions at the same time. And if we push this one down, support reaction at point E and E doesn't allow this rod to rotate. Therefore, our influence line is going to look like this shape. And since the impulse displacement is unit, we're going to have -1 here, and the other side can be easily calculated through the mathematics. So this is going to be the influence line for VC. And the last one is influence line for bending moment at point E. We said for bending moment, if we want to draw the influence line through qualitative approach, we are going to have one internal hinge, and then we are going to impose a bending moment to that internal hinge and look into the deformed shape. So this bending moment is going to have a clockwise shape in the right side of the hinge and counterclockwise in the left side. So for the right side, if I apply the clockwise direction bending moment, our beam is going to have a rotation similar to this one. However, left side, you need to see whether it can rotate or not. So you can see there is a support at point D and there is a support at point E. And these two support reaction is not going to allow for rod ED to move. And right ED, if right ED doesn't move, the other part of the beam also cannot move. Therefore, we are going to have a deformed shape similar to this one. And since we said the rotation is going to impose 1 radian. The bending moment is going to impose 1 radian rotation. So since you know the length is 2 meters, 2 multiplied by 1 is going to give you -2. So therefore, this is going to be the shape of influence line for bending moment at point E. So that's why you can see here. So we draw the influence lines, and now we are going to calculate the maximum VC and ME for these 2-point loads that is given to us. Since the first one is self-weight, so for the calculation of VC, self-weight is going to be all over the span, similar to this one that you can see. This is our influence line, so we put this one all over the span. Therefore, we need to calculate these two areas. One of them is positive, one of them is negative. And this is what has been done already. A1, the positive side is 0.33 meters square, and then the negative side is going to be -3 meters square. So you can see the negative one is significantly larger than the positive side. Therefore, under the uniform load that is all over the span, this self-weight, we are going to have a negative value for our influence line. Therefore, for the point load, if they want to become maximum shear force, if they want to impose maximum shear force at point C, they should be placed in the negative side of the graph, because from the uniform load, the value of shear force definitely will be negative. And if they are placed in the positive side, they are going to reduce the value of this negative value. So this is why we need to find in the negative side of the graph the location that impose maximum negative value. So one of the location is similar to what you can see here, meaning the 5 ton is at point 1 and the 1 ton is going to be after that. Since the distance is given to us 3 meters, so if the 5 ton is here at point C, 1 ton is 1 meter before point D. But since the value of there is 0, so 1 ton doesn't impose anything, and we have only 5 tons. So 5 multiplied by -1 is going to be given to us -5. Another scenario that you can also examine is the case that when we have 1 ton here and 5 ton is 3 meters behind it, and which the value is 0.5, the value of influence line. So 3 multiplied by 0.5 is 1.5, and 1 multiplied by 1 is 1. It gives us 2.5. So this 2.5, -2.5, is smaller than -5. Therefore, this scenario is going to provide larger shear force. And the first one, this one is not the critical one. So right now we have this -5, and we need to sum it. This is coming from the point loads, moving point loads. And then we need to sum up with the negative value that we get from our uniform load. And totally we get -45.05. So this is how we can calculate the maximum. If, let's say, the area of positive side was larger than the negative one, so in that case, you need to put your point load to the positive side. This way, the shear force is going to be the largest one. Or another way is to do the calculation for negative, V negative, and V positive, and then see which one is larger, and then it's going to be obviously -45. So it is up to you, but you can always come up with a smart solution by looking into the areas and see which area is larger, negative area or positive area, and then put the location of your point load at the place that can give you a largest negative or positive based on the self-weight. Okay, so this was for the calculation of shear force. For the bending moment, also we have the same situation. We have only negative bending moment, and there is no positive area. Therefore, the calculation is going to be much easier. So we need to calculate this area, A3, and then multiply it to the intensity of uniform load, 15. This is the one that we have done here, and gives us basically the support, the bending moment due to the uniform load. And then for point load, you may have two different conditions. One of them is the one that can be seen here, meaning one of the point load is at the end of the cantilever, and the second one has already passed the bridge. So for this case, you get 5 multiplied by -2, which is -10. You may examine another case in which you may have, since this one is basically 2 meters and the distance between our point load is 3 meters, according to the equation, according to the test, 3 meters here. So the second case definitely is not going to be critical case in which that you have the 1 here and 5 is here, 3 meters, meaning 1 meter behind this support. So you get only 1 multiplied by -2, which is much smaller than 5 multiplied by -2. So you can examine different cases to see which one is the critical one. So this one is critical. So 5 multiplied by -2 plus the one that comes from the uniform load, it totally gives you -40. So you can see we easily calculated the maximum shear force and maximum bending moment. Okay, so these two examples just show to you that how you can calculate the influence lines and how you can calculate the maximum shear force and maximum bending moment. So if you had any question regarding the calculation of shear force and bending moment, you can ask in our next class. Now, in the continuation of our lecture, I will switch to another topic, which is also very important for you because normally you have one example, one question in the final exam, and you need to know how to solve it. And also in your future subjects, you are going to use this basically technique. And this is basically about plastic analysis of a structure. So I'm going to share that one with you. Plastic analysis is the notes have been already uploaded in the e-learning. So try to watch it carefully. You can learn it from there. Let me share the lecture with you. Okay. Okay, let me enlarge it. Okay. So this is the last basically subject of this lecture, plastic analysis. As I said, in the final exam, normally you have one compulsory question to answer from this part. Let's have some introduction to see why we need plastic analysis. So far, whatever you have learned in this course is valid when you are in the elastic range. What does it mean, elastic range? Okay, we need to go back a little bit to strength of material. Most of you have done tensile strength test in which you put one rod inside the tensile machine and you impose force until it reaches to the rupture. So you can easily draw a graph that shows the stress over strain. The force divided by the cross section gives you the stress, and elongation of the bar as you apply the force shows the strain. So if you draw this curve, you are going to see is going to be there's going to be a linear relationship between stress and strain until a specific range. This is what we call it elastic range. So the technique that you have learned right now, like moment distribution, slope deflection, and force method, they are valid only when the stresses inside your cross section is within this range. If it is larger than this, those techniques cannot work, and you need to go through plastic analysis. Meaning when the stress is larger than sigma y, which is the yield stress of your material. So if you increase the force more than the yield point, you may have a graph like this. For a specific duration, you can see that without increasing the force, you're having a long or large elongation inside your bar. So this is the indication of yield, and sometimes some material shows strain hardening until they reach to the ultimate stress and ultimate strain. So the plastic analysis basically is working in this range, in the plastic range, and we want to see how we can design our structural elements when they reach to this level of stress. So one of the important things that you need to know about plastic analysis is that plastic analysis provides much more economical cross-section for our beams and columns. One of the reasons is that you're using a higher level of stress inside your design. However, when it comes to elastic method, normally you are around 60 or 70% of sigma y is the range that you accept for the stress inside your cross section. Therefore, you have a smaller beam size, column size compared to the time that you use elastic method. You should also understand that due to some reason that we are going to discuss it later, plastic analysis is considered to be suitable for indeterminate structure. And determinate structures are not that much suitable for plastic analysis, and there's not going to be too much changes in the cross-section of determinate structure if they are designed based on plastic analysis. Okay, before we go through the plastic analysis itself, we need to see what is happening inside the cross-section of beams and columns when stress increases little by little until it reaches to yield and until it passes the yield stage. So this is what we are going to discuss in our next slides. So in the beginning, we are going to assume that we have a beam, simply supported beam, similar to what you can see here. And then we are going to impose a unit load, or a point load to the mid span of this beam. The p-value is going to change little by little. So at first, we impose a very small force. Of course, the bending moment diagram is going to look like the one that you can see here. And the cross-section of this beam can be any shape. We assume that it may look like something similar to what I have drawn here, but it can be circle, it can be triangle, it can be rectangle, it can be I-shape or any other shape. So our job is to draw the stress diagram inside this cross-section. When you are in the linear region of your stress, you can always show the stress distribution in the cross-section through this graph. If you look, we have here the neutral axis that shows the bending axis of the cross-section. And then above this line, normally we have tensile stress. And below this line, we have a compressive stress. And this stress in the cross-section can be related to the bending moment through the equation that all of you know. Sigma, which is the stress, equals to bending moment multiplied by y. Y is the height in which you are calculating the stress, and I is the moment of inertia of your cross-section. So this equation is valid as long as you are inside the elastic region. So the moment that you increase the bending moment, of course, consequently, the stress is going to increase. And of course, if you have a larger cross-section that has larger I, the stress is going to be smaller compared to the cross-section that have a smaller size because their I is going to be different. Okay, and now let's increase the force a little bit more until the first fiber inside of our cross-section reaches to the yield stress. So this is why we have shown here the upper part equals to sigma y. Sigma y is the yield stress of your material. For example, if you have a mild steel, it can be around 300 megapascal, 240 to 300 megapascal. So the moment that the stress reaches to that value, we call it yield stress. So this shape is showing the case that one of the fiber has reached to its value. At this case, we call the bending moment to be a yield bending moment, and we show it with My. So My is the condition in which only one of the fiber in the cross-section has reached to its yield strength or yield stress. And in order to calculate or relate this My to the bending moment that you have in your beam, you can always say My of bending moment of your beam equals to sigma y, which is the yield stress of your material, multiplied by S. S is section modulus, and we can show it as I over C. I is moment of inertia, and C is the distance between the neutral axis and the outmost fiber of your cross-section. So through this equation, you can calculate and relate this stress to the bending moment that you have in your beam. Now we increase the force in that beam that I showed you in the beginning. Little by little, when the force increases, the bending moment increases, and at the same time, more and more fibers are going to reach to the yield value. At one time, almost all of your cross sections fiber have reached the yield. Therefore, the diagram of stress in the section is going to look like two blocks of rectangular shape. And the value of stress in both blocks is reaching to sigma y. So this is a time that we call it, we have reached to plastic moment. And plastic hinge basically forms at this time. So after this, you're going to hear we're talking about plastic hinge and plastic moment. So when we're talking about plastic hinge and plastic moment, we are referring to this stage in which all the fibers inside your cross-section have reached to the yield strength. So if you want to calculate the bending moment in that condition, this MP does not follow this equation anymore. So in order to calculate the MP based on the cross-section size and material properties, we can use this graph. So you can see here the cross-section of your beam can be divided into two parts, the tensile part and the compressive part. So for the upper part, you can find the centroid. For the lower part, also you can find the centroid. And the distance between these two can be shown by y bar C and y bar T. And here you can calculate how much is this A, how much is this A. If you multiply this A to sigma y, you get 1/4 over there. And if you multiply this area to sigma y, you can get another force. So distance between these two forces, as I said, can be represented by these y bar C and y bar T. So these two forces basically is making a coupling bending moment about the neutral axis. And this is what we call it MP. So MP can be calculated by multiplication of A over 2 multiplied by sigma y multiplied by this height, which is yc plus yt. If you have basically a cross-section that has a rectangular cross-section, a beam that has rectangular cross-section, we can represent this equation by a more simplified equation. For MP, we can say that MP equals to always Zp multiplied by sigma y. And Zp is basically this E over 2 multiplied by yc plus yt. So sigma y is there, and these two multiplied by A over 2 is Zp. Zp is a plastic modulus of your section and depends on the shape of your structure. For a rectangular shape cross sections, Zp can be calculated by this equation. And for a circular shape cross section, Zp can be calculated by this equation. Therefore, if you know what is the yield strength of your material, like as I said, mild steel is 300, and you know the size of your cross section, B and D, how much it is, you can put it inside this equation and you can calculate how much is its MP. Or you can put it inside this equation and you can get how much is its My. For your information, MP is always larger than My, meaning for a given cross section like a rectangular section, from the time that the first fiber reaches to yield until the time that all fibers reach to yield, we have a large distance. And that depends on the shape of your cross section. The value of MP over My is considered to be the ratio of MP over My is referred to it as shape factor. Shape factor is MP over My. And as I said, for different cross sections, this ratio is a different value. If you have a rectangular cross section, the value is 1.5, meaning from the time that the first fiber reaches to the yield until the time that all fibers reaches to yield, around 1.5 times more bending moment we need. But when it comes to I-shape or C-shape cross sections, it is around 15% to 70% larger. For your information, the larger is the shape factor, is the better for the plastic analysis and design. The reason is that when you have a larger shape factor, that means you have a larger time to leave the building before your structure collapses. Because when you reach to My at this bending moment, when the force increases and it reaches to My, you'll see a large deflection inside your beam. So if this large deflection is going to prolong until you reach to a very large MP, then collapse occur. You have more time to live. However, if MY and MP are very close, then the moment that you see the crack, the beam is going to collapse. Therefore, you don't have time to leave the structure. That's why structural cross sections that gives us a larger shape factor are more considered to be the suitable for our plastic analysis and plastic design. Okay, these equations are given to you. In the future, if you wanted to calculate the MP of a section, you just need to refer to the shape of that, calculate its ZP, plastic modulus, and put it inside your equation, you can get the MP. So don't forget, MP is a plastic moment inside your beam, and we cannot reach to a value larger than that. The moment that your beam reaches to MP, the plastic hinge is going to form inside your cross section, and the bending moment is not going to be larger than that after that. So the moment that you reach to MP, you have reached the largest bending moment that your beam can carry. Okay, the question right now is that when our structure is going to collapse, or how it's going to be if we increase the force inside our structure like a beam. I'm not going to explain this one more in details when it comes to the next slides, but here, just to make you familiar with our plastic analysis, we just give you a very simple example of failure due to the formation of plastic hinge inside our beam. Okay, what you can see in the left side is a beam which has been subjected to the point load, and the point load is exactly in the mid-span of that beam. So if you look carefully, you can see we have a bending moment diagram similar to the dashed line. And the moment that the P is small, actually the beam is going to deflect in the elastic range. However, when the P is getting larger and larger, this is the time that the bending moment in this location under the load reaches to MP. As we said, MP is the largest bending moment that the beam can carry. So the moment that we reach to MP, this is the time that we are going to have one plastic hinge over there. This plastic hinge basically is like a hinge, meaning it cannot tolerate any additional bending moment, and it is going to have a large rotation in that location. And the deflected shape of our beam, the moment that we reach to MP, is going to look like the one that you see here. For your information, we assume that at the time that we reach to MP, we can show the deflected shape with a straight line, meaning there is no bending moment, there is no deflection inside the line. It's just on a straight line. Therefore, we can do some mathematical calculation here in order to calculate what is the critical load that shows the collapse of the beam, that corresponds to the collapse of this beam. So if this is the deflected shape at the time that we reach to MP, or at the time that collapse occurs, we can say that we have some deflection under these point load that we have applied. That deflection, we can show it with delta. You know, from mathematics, this delta also can be calculated based on the rotation of this beam. Since the load has been applied exactly to the center of the beam and it is symmetrical from both sides, so the rotation at the time of collapse at both sides equal to a theta like to angle like theta. So this angle and this angle will be exactly similar due to the symmetry of the loading and the beam. And according again to mathematics, if you have an external angle of a triangle, the value of that external angle is always equal to the summation of two internal angles. So this theta plus this theta always equals to this angle. So this angle basically shows how much is the rotation of this plastic hinge. Because in the beginning, the beam was straight, and at the time of collapse, it's going to have a deflected shape like this. In other words, at the time of collapse, this hinge has shown around 2 theta rotation. However, our rotation at this side and this side is having only around theta, half of the rotation that occur here. This is based on mathematics. Okay, so why I said all these things? Because the technique that we use in order to calculate this critical load is based on kinematic approach. And the kinematic approach says that basically internal work done by this plastic hinge should equal to the external work done by this force. You know, work is always force multiplied by displacement. Therefore, if I want to calculate how much external work has been done by this point load until we reach to collapse, I just need to multiply its intensity to the deflection that occur under the point load, meaning PC multiplied by delta is the external work done by this PC from beginning until the collapse condition. So we can easily calculate the external work. P multiplied by delta is the work that done by this. I can replace this delta with the multiplication of L over 2 multiplied by theta. According to mathematics, if you have a small angle, this L2 multiplied by theta equals to delta. So that's what we have done here. So you can see our external work is PL theta over 2 according to this calculation. How about internal work? Here we have two hinges, and these hinges have been there from the beginning. Therefore, they haven't done any work. However, since we have generated a plastic hinge here, so we have some internal work done by this plastic hinge. How much is the bending moment at this plastic hinge location is MP. According to what I said, the bending moment cannot be more than MP. The moment that it reaches to MP, we get one plastic hinge. Therefore, internal work is going to be this bending moment multiplied by its rotation. Since we have 2 theta rotation here, this 2 theta is compared to the time that the beam was completely straight, horizontal. It has rotated 2 theta, and the bending moment here is equal to MP. So MP multiplied by 2 theta is the internal work that has been done at the time of collapse. So this is what you see here, MP multiplied by 2 theta. As I said, according to kinematic approach, external work should equal to internal work. Otherwise, the beam cannot stand in the steady condition. Therefore, we can write down WE, internal work, equals to external work. And then if you equal these two to each other, from there you can see that this P, which is the P critical, equals to 4MP divided by L. So the critical load that make this beam to collapse equals to 4 times 4 multiplied by MP, the plastic moment of the beam, divided by its L. So this calculation shows to me that if you have a larger MP, how we can get larger MP? According to what we saw up here, larger MP means a larger cross-section, because larger cross-section is going to have larger ZP. Therefore, if you have larger MP, meaning larger cross-section, the critical load, of course, is going to be a larger. Or if you have a smaller span, you will have a larger PC. Another thing that is going to influence this PC is the support condition. Here, our support condition is pin and roller, and the beam considered to be a determinate beam. If you remember, just now I said to you that plastic analysis is going to be more useful when we have indeterminate beam. And indeterminate beam is more suitable for application of plastic analysis. One of the reasons is that, you will see later, in order to reach to the collapse of a beam, we always need to have 3 hinges in one span. This is what we call it beam mechanism. In the column also is the same, meaning if you have a column, the moment that you have 3 hinges in one column, 3 hinges in one beam, the beam is going to be in the collapse condition and cannot tolerate any additional force. In the beginning of analysis, when the force was small, we had only 2 hinges, and these hinges were due to the support. However, the moment that the force increases and the bending moment reaches to MP, this is the time that one plastic hinge is going to form due to the bending moment. And then we are going to have 3 hinges, one due to the bending moment that has reached to MP, and then the other 2 due to the support condition. So 3 hinges basically in one span, and the beam is going to reach to its collapse condition. However, if for the same case, let's say for the same beam, that is subjected to the same load, if the support condition was instead of pin or roller, it was fixed support. So you can see in the beginning of analysis, we don't have any hinge. In order to make this beam to reach to the collapse condition, we needed to have basically 3 plastic hinges. In that case, the beam could reach to its collapse condition. So if you want to calculate the P critical for this beam with the same length as the first one, you can use the same technique that we had here. So again, according to the basically symmetricity, this angle is going to be theta, this angle is going to be theta, and here we have 2 theta as the rotation angle. What is making difference between the previous case and this case is that in the previous case, when we were calculating the internal forces, internal work, we said since from the beginning these two were hinged, they didn't do any additional work for us. That's why it didn't come into the calculation of internal work. However, in this case, since there is no hinge and the hinge is formed due to the bending moment, therefore there is going to be some work done by the hinges in the support. So if I want to write down basically the internal work that has been done by the support, so it's going to change my calculation to MP2 theta, MP theta, and MP theta, meaning these two are also should be included in the calculation of the internal force. So MP theta, another MP theta is going to be also added here. Because in this case, we have to have again 3 hinges to make the beam collapse. And as I said, since there is no hinge in the support, we need to wait until the bending moment reaches to MP. So our internal work is going to be basically 4 MP theta. So it's going to be 4 MP theta. However, external force is the same because we have only P multiplied by delta, and this delta can be replaced L over 2 multiplied by theta. So this doesn't change because it's the same calculation, force multiplied by its displacement. But the internal work is going to increase. So if you make these two equal, then this is the time that you can see the value of P critical increases to 8 MP over L. That means twice larger force a beam with fixed support can carry until the time that it reaches to collapse, compared to the time that the hinge, that the support are pin and roller. So this beam with the same cross section can tolerate twice larger force compared to the beam that is pinned. So this is why if you have indeterminate structure, we are going to have a larger force for the collapse condition. Or in other words, you can have a smaller cross section for reaching to the same PC. Meaning here, if you calculate how much is MP based on PC, is going to be PCL divided by 8. However, in the first case, it's going to be PCL divided by 4. So you can use a small cross section when you have fixed support compared to the time that you have pin support. You will see this one more in detail in our next slide. So you just need to go to the next slide. Okay, so let's go to the next slide. In the next slide, what we are going to do is to see the collapse mechanism that exists inside structures. So one of the collapse mechanisms that just now I explained is the beam mechanism. So in the beam mechanism, we need to have 3 hinges in one span to make the structure collapse. If you have 2 hinges only, the beam cannot collapse. If you have 1 hinges, the beam cannot collapse. But if you have 3 hinges, your structure cannot tolerate any additional force, because in reality also, if you assume inside your mind that you have a beam connected to each other by 3 hinges, this beam can easily deflect or down. Therefore, it cannot tolerate any force. But in order to reach to these 3 hinges, if your support is fixed support at both sides, you need to make 3 plastic hinges. However, if you have pin support, by having only one plastic hinge, your structure is going to collapse because the other two ends of your beam already cannot tolerate any bending moment and are hinged. Therefore, one plastic hinge can make your beam reaching collapse condition. Okay, so this is what we call it a beam mechanism. Similarly, if this one is vertical and become a column, the same issue, meaning you need to have 3 hinges to make a column collapse. Doesn't matter if it is beam or column, as long as you have 3 hinges in one span, we have collapse. Another case that we will see later on is sway mechanism, panel or sway mechanism. In panel mechanism, we need to have at least 4 hinges to make our structure collapse, according to what you see here. So again, if your support condition are basically pin condition, these two are already hinged, and you need to have 2 plastic hinge for the frame to collapse. But if they are fixed, you need to make 4 plastic hinge, reach to 4 plastic hinge, then your structure is going to collapse. Or even if you have a frame that one side is pinned, one side is fixed. So in order to make this collapse, you need to have 1 plastic hinge here, 1 plastic hinge here, and 1 plastic hinge here. Because this one is already hinged. So 3 plastic hinge plus 1 hinge is going to be totally 4 hinges. So depending on the support condition, but in general, doesn't matter what is the condition of your support, you need to have 4 hinge. If your support condition is fixed, this 4 is going to be 4 plastic hinge. If your support condition is pin, this 4 hinge is going to be 2 plastic hinge and 2 hinges due to the support. And it doesn't matter that your frame is having an inclined roof or it's going to be a straight roof, doesn't matter. Again, you need to have 4 hinges. Okay, so this one was a sway or panel mechanism, and it's applied when you have a frame. There are cases that your load basically is not applied exactly to the joint. Like you have a frame and your load is applied to the column, or your load has been applied to the beam together with the lateral load. In that condition, we have a combined mechanism. Combined mechanism. What does it mean, combined mechanism? Combined mechanism means a combination of sway and beam or column mechanism. So again, for that case, you need also to have 4 hinges. For the combined mechanism, you need to have 4 hinges to make your structure collapse. So it's going to be, for example, if I want to show you what I mean, for example, we have a frame like this, and you have applied 1 point load to the column. So for this structure to reach to the collapse, in the collapse condition, let's say it's going to be like this, you need to have 4 hinges, again, in here, and at the base. So this is a combination. Sorry, I made a mistake here. Need to try again. One of the hinges is going to be at the location of the load that you have applied. For example, if this is your frame and you have applied the load to the column, your beam may collapse in condition like this one. Okay, one of the hinges, you need to have again 4 plastic hinge, and one of the hinge can be here, another one can be up here, another one can be here, like another one can be here. So these hinges basically occur at the location of maximum bending moment. And you will see in the next examples that we are going to solve how we can determine the location of these plastic hinges. But regardless, the load is at the beam or column. For the sway mechanism, you need to have 4 hinges. And if you have pin condition, 2 hinges comes from your support, and 2 hinges is going to be the plastic hinge that occurs inside your structure due to the bending moment. If you have a beam mechanism, the beam mechanism needs always 3 hinges in one span. And if you have a support, which is pin, you need only one plastic hinge together with two hinges at the support to make your structure collapse. So that's basically the story of a collapse mechanism. So we have three different collapse mechanisms: beam and column mechanism, sway mechanism, and combine mechanism. Beam is the time that you have only one load in one span, and you need to have three hinges. Sway is when you have a frame and it is subjected to a lateral load, and you need to have four hinges. And combine mechanism is when you have a point load applied or uniform load applied to a beam or column, and together you have sway. So it is a combination of beam and sway when we are talking about combined mechanism. So these are the three main mechanisms that exist in a mechanism of collapse mechanism of structures. Okay, sometimes just now you saw we calculated the P critical, the critical force that makes your structure collapse. In reality, we don't want our structure collapse under the load that we apply to a structure. Let's say you are designing a beam, and you know there is, let's say, a weight of 10 kilonewton applied to the median span. So you don't want to design a cross section that due to this 10, your beam reaches to collapse. So normally we use a safety factor that we call it plastic load factor, and we show it with lambda P. And we normally multiply that lambda P to show some safety factor against collapse. And this is the case that we use it for the design. And normally in this course that we teach to you, we are not talking about this plastic load factor. And in the exam and test, we normally don't give you any safety factor, and we just want you to calculate the critical load without any safety factor. But just for your information, I have put this one here that when you want to design, we always consider a safety factor against collapse. Okay, just now we saw one simple example that we use kinematic approach in order to calculate this critical load. Here again, I want to show you that how we can use this kinematic approach in order to calculate the critical load of a fixed support beam, which is subjected to uniform load. Before this, we had point load here, and right now we want to see how we can use this kinematic approach in order to calculate the W critical under fixed support condition. So as we said, since we have only a beam here, in order to calculate the critical load, we need to have three hinges. And these three hinges is going to happen when our bending moment reaches to MP. But in order to determine where is the location, we need to look into the bending moment diagram. So if you draw the bending moment diagram of this beam, you can see the maximum bending moments occurring at both corners of this beam, and the maximum negative bending moment and the maximum positive is in the middle of the span. Therefore, if there is going to be basically plastic hinge occurring in this beam under the load when we increase the W, is going to be both ends when we have maximum bending moment negative. And then we have also one plastic hinge in the middle of the span, because the bending moment here is maximum and the plastic hinge can occur here. So at the time of collapse, this is going to be the deformed shape of our beam. Three plastic hinges have been formed due to this W load, two hinges at both ends and one hinge right in the middle of the span. So these three are occurring not to the support condition, which is P. It is occurring because the bending moment there increases until it reaches to MP value. So right now we know that the bending moment here is MP, here is MP, and here is also MP. And then from mathematics and symmetry of the beam, also we can know that the angle at the time of collapse can be assumed to be theta here, and the other one also is going to be similar value equal to theta. And the angle of rotation that shows the rotation of plastic hinge in the middle of the span is the summation of these two and equals to 2 theta. And then again, the deflected shape of this beam equals to delta in the mid span. So this delta can be written according to this equation, L over 2 from here to here is L over 2 multiplied by this theta equals to delta. So if I want to calculate the internal work, it's going to be this MP multiplied by this theta, this MP multiplied by 2 theta, and this MP multiplied by theta, meaning bending moment multiplied by its rotation at each plastic hinge. So this is what you can see, and totally we get 4 MP divided by theta. Now for external work, if the load was a point load, we could always say P multiplied by delta is the external load. But right now, we have a uniform load, and it is not similar to the point load that we saw in the previous slide. So when you have a uniform load, basically what you need to do is to calculate the average value of your force that has been applied to your beam. So the calculation is similar to previous example, meaning you multiply W to its length. So that gives us a resultant force. This is WL. And this WL multiplied by delta is basically the work that has been done in the midspan. But since we have force from beginning until the end, and it's not concentrated here, we multiply this one to 1/2, an average, to take into account the fact that the load is not a point load and it is uniform load. So this 1/2 is just because our load is a uniform load. So WL is the resultant force multiplied by delta. As you can see, delta equals to L/2 multiplied by theta. So this is delta, and multiplied by 1/2, which is the average of the load that has been applied. So you get in the external work, you get internal work, and then you, according to kinematic approach, internal work should equal to external work, and then from there you get MP equals to this value, or you can write down W critical is 16 MP, W critical equals to 16 MP divided by WL, divided by L power 2. So you can see in order to reach to collapse condition, the W should reach to this amount. And again, if you increase MP, WC increase. If you decrease L, WC is going to increase. And if you know how much is your W here, let's say W is 1 kilonewton per meter, then you know how much is W, you put your W here, then from there you can calculate how much MP you need. So if you know how much MP you need, let's say you need to have 10 kilonewton meter as MP, then you know MP equals to ZP according to previous slides multiplied by sigma Y. And ZP depends on the cross section of your beam. So if it is a rectangular section, you know how much is ZP, so you can estimate, you can assume a value for the width and height and put inside this equation and see how much MP you get and compare it with this 10. And if it was larger, so your beam is going to stand the force. And of course, this W needs to multiply to a safety factor of lambda P. This way you're sure that your beam is not going to collapse under the load. So this is a very simple example of how we do calculation for, or how we analyze our beam under the plastic condition when they reach to the collapse stage. We are going to see more example in our next class when we start talking about continuous beam. And I will stop here this lecture, and we will continue in our next class about continuous beam and also frames. So please watch this video carefully, and in our next class we may have a quiz. So from whatever I explained until so far, therefore all of you need to watch the video carefully. This way I'm sure that whatever I have taught you within this video is already understood by all of you and you're ready to continue the subject. Okay, so see you in our next class. I stop recording and you can watch the video by referring to our e-learning website.